Welcome to Physics 2212 Lab 5 Magnetic Braking with Faraday lab report. My name is Kenneth Alexander Jenkins. The introduction for today's lab is to explore Faraday's law using a magnet and aluminum foil in combination with computational modeling. The fundamental principles used in today's lab are Faraday's law, magnetic force on a wire, the Biot-Savart law, and Newton's three laws of motion. As a preview of the results, the experimental average was 0.706 seconds, and the computational estimated average was 1.047 seconds. Introductions, models, and assumptions. Models and assumptions for this lab, as the bar magnet is treated as and modeled as a dipole for the purpose of calculations in order to properly apply the Biot-Savart law correctly. The definitions of systems and surroundings for this lab include systems as the bar magnet, and surroundings as the aluminum foil and everything else. Experimental procedure step 1. Mark the north pole of the bar magnet with a piece of tape or marker. Step 2. Measure the mass of the magnet in kilograms. Step 3. Measure the width, inner radius of the tube, the length of the tube of aluminum foil in centimeters. Step 4. Carefully drop the magnet through the tube 5 times in a row, recording the time that it takes for the magnet to fall through in seconds. Be sure that the tube is held still and the magnet is dropped from rest. Step 5. Compare the results with a computational model of the magnet-aluminum interaction in GlowScript. Introduction, Initial Conditions, and Measurements, Part 1. Assume the magnet falls from rest. Length, width, and radius of the aluminum foil were given from the outer of the packaging, and the dipole moment was given from lab 3. The measured conditions of the length of the tube were 0.45 meters, the width of the tube is 0.003 meters, the inner radius was 0.035 meters, mass of the magnet was 0.03 kilograms, and the dipole moment was 1.200227 am squared. The average measured time for this lab was 0.706 seconds. As on the right, you can see the trial and the time. Experimental procedure step 2. Physical experiment was modeled and replicated GlowScript. The starter code was provided and edited for this lab. Computational modeling revealed that the magnet fell for 1.047 seconds. A link to the GlowScript model could be found right here. On the left, you can see a capture of the actual model itself. Here's the code. On the leftmost panel, I have marked what I did. For the first 2 lines, I've edited the starter code, and then I've also added measured values. On the right picture, I've also added measured values, and then I've also used the given in starter code. The code continued. I've added the previous calculated B dipole code from lab 3. I've also added code to calculate the magnetic field. On the right, you can see what I've done to each line. Most of it was given in the starter code. However, some stuff, like I've adjusted for gravity. I've also fixed the B force formula, and as well as added the B ring plus B force code and added code for the net force. The most important thing about this lab and where I used Newton's laws were at line 178, where I used Newton's laws to calculate the velocity of the magnet. What if and why questions? What if the resistivity of the conductors were reduced as close to possible as 0? What would the dynamics of a flowing magnet change? Since the magnetic flux stays constant, the electromagnetic field produced by the flowing magnet would also stay constant. This would cause the current to increase, which in turn would create more magnetic force against the falling magnet. What if holes or slots were cut into the tube? How could this affect the ring currents in your model? It likely would have caused the magnet to fall faster, since there would be fewer rings or area of foil for the induced current to flow through and resist the force of gravity on the magnet. Similarities and differences, modeling discrepancies. A bar magnet's field typically very closely models that of a magnetic dipole, so our choice of modeling likely yielded very accurate results. Computational modeling in GlowScript does not take into account air resistance or the purity of aluminum foil. This alone likely contributed to the differences between calculated and observed times. Conclusion: potential sources of error. Electronics emitting fields and induced currents causing induced currents in the aluminum foil before the magnet was dropped. The magnet not being dropped at rest, or the movement of the tube during the free fall of the magnet. Measurement errors, specifically since there was only one observer recording times and dropping the magnet at the same time. And impure aluminum foil and air resistance not being taken into account with computational modeling. Conclusions. Both the Biot-Savart law and distance dependence can be applied to a bar magnet with fairly accurate results using computational modeling. Bar magnets can be used to accurately model magnetic dipoles, and air resistance is not always negligible, but almost always provides results that are in the ballpark of actual experimental results.